biomedical engineering from the University of Pisa in 2007, and a PhD degree in biorobotics from School of Superior Santana. So he's a member of the IEEE of the Engineering and Medicine and Biology Society and of the Robotics and Automation Society. So he has been and currently is involved in EU-funded projects with a main focus on the development of soft robotics technologies. So his talk is Virtualizing soft material. So this is a workshop, but we can accept the question at the end of his talk. So, okay, we'd like to welcome him to this seasonal school. So, Matteo, could you share your screen?
Yes, sure. Just a second. Can you see my screen?
Yes. Okay. Please start your presentation.
Great. Thank you very much. And thank you very much for your nice introduction. And I'm quite sure that Cecilia, in her previous talk, convinced you about the importance of the materials, the materials that we are using for our robots, and that the body matters, right? So maybe we can see how can we bring the characteristics of real materials into a virtual environment. And this is what this talk is going to be about. Okay, so elastomers in general are kind of soft materials that we usually use in soft robotics. They are polymers, and polymers are actually usually classified in two main groups, thermoplastic and thermoset. The difference is that thermoplastic materials are usually based on polymer chains that are tangled, but there are no cross links between the chains. So they rely on weak forces of attraction between those chains. And if heat is applied, actually the overall effect is that they soften, they become softer. On the other side, we have thermoset materials that have cross links that are holding together the polymer chains. So they are really connecting those chains. And these are actually not breaking by heat. So they remain hard, they remain, they still remain there also when you apply heat. But there's also another classification of polymers that are based on physical properties that is about the kind of deformation, specifically on the amount of deformation. And the elastomers are actually classified in this different group. And specifically, elastomers are polymers that exhibit rubber-like plasticity. So elastomers include natural and synthetic rubbers, are often amorphous, and are composed of long molecular chains that are highly twisted. So you can see here an example of an undeformed polymer that has this twisted, coiled, and randomly oriented chains. They can be partially straightened when the material is stretched, then twisted under this tensile load. And they are able to revert to their original configuration when the loading condition is removed. Rubber elasticity is mainly due to the flexibility of the chains it is composed of, the entanglement of the chains, and the interaction between the chains. There is also one last point is about a reduction in entropy. So the reduction of the other way around, the increase of the order the chains are arranged, and not because of the stretching of molecular bonds that is the case of metals that rely on high level of crystalline. Elastomers have peculiar properties. They can undergo very large deformations that is fully recoverable usually. They usually go beyond 100%, but also even to 1000%. They usually undergo very little volume change when it is deformed. This is why we are usually considering them nearly incompressible. And as you can see here, I'm reporting say, the general and, ideal behavior, mechanical behavior of an elastomer. As you can see, it is highly nonlinear, so it doesn't, it cannot be represented through the Hooke's law anymore. The peculiarity of this plot is that actually it is composed of mainly two parts, especially the tension part. We have a very first part that is more linear, let's say, but it is for very limited deformations. Then we have sort of softening here, and you can see how the slope of the curve is lowering. And it is due to the intermediate deformation and due to the straightening of the polymeric chains. But then after, a certain amount of deformation, let's say when the deformation is starting to be remarkable, we have an increase of the stiffening again. This is especially due to the long chains, the polymeric chains, that start to be stretched, and this is the cause of this hardening effect. This is a very typical stress strain curve that is derived from a characterization of an elastomer. And as you can see, there are some peculiar characteristics. They differ related to, on the basis on four main parameters that are the method of manufacturing of the samples you are testing, the curing time that you use to manufacture, environmental conditions, actually as in all the cases where temperature and humidity may have an effect, and also aging, if the time that is elapsing since the time you recured, you fabricated. You can notice that there are some peculiarities. There is, of course, first of all, some viscosity, viscoelasticity that is very visible, and that is also leading to hysteresis, which is of course related to the velocity we are using in the testing conditions of the material. You can see that there is this first part of the field that is quite different from the rest of the test, and we are going to see that more in detail why. But you can also anticipate that there is this very initial effect of a permanent set, so the shift to the zero after the first cycle, loading cycle is applied. But after a few cycles, you see that actually they are all overlapping, meaning that the mechanical properties are stabilized. Going a little bit more in detail about, especially the permanent set. Zoom in a little bit here. So the first cycles are more or less what you can see here in red. So you see the very first way you stretch, you load your material, is actually a very different curve with respect to all the arms. But actually what happens here is that the first time that you are making your material experiencing the stretch, you are actually really damaging the material. It is really damages at the very microscale level, so you are not really able to see that. But what happens is that some of the cross links internally are really broken. So this means that after the first loading condition is applied, when you go back and you remove the loading condition, you don't go, to the original zero, but you have a new zero, that is this one in this case. And if you go back to your loading condition and forth to the zero condition, you are starting cycling in these new conditions. So this is a path that you are not going to see anymore. So you are looking at this behavior only once in the lifetime of the material. But then, if you, for any reason, apply loading conditions that are different from the previous maximum that you applied, you have this blue line that first part is equal to the red path, but then it changes, right? And then if you go back again and remove loading conditions, you don't go back to zero again, but you set a new 0. This is because in this other path, you've broken other crossroads. This is something that is irreversible. Then you still have elasticity, but to a new 0, and so on. So if you then increase once more the maximum loading condition you're applying, you set the new 0, and you have a new curve. So it is extremely important to assess and to know what is the maximum loading condition that you are going to use in your application. So because this is what you need also to characterize the material. This effect of these damages that are in sequence in cascade applied to the material is known as Marlin's effect. Do you see this? I'm visualizing something here, but I don't know if you see that. So, sorry for the interruption. So let me go through the way to virtualize this kind of behavior. As you saw, this highly nonlinear behavior is not something that a linear elastic model can really catch. So there are some hyperelastic models that are instead used for this, and they are able to model this very peculiar stress strain behavior. There are some key assumptions that we should keep in our mind. That the material is assumed to behave isotropically, so it means that whatever is the direction of the loading condition is going to behave this.
Matteo,
Yes?
Sorry for interrupting.
Yeah.
So your voice is a little bit noisy, or so some students cannot hear. So could you check your microphone? Or?
Maybe if I keep it a little bit closer. So already at the maximum of performance, I can check. Is it understandable at least, or it is really not acceptable? Because I don't know if I can do much better than this.
It's almost the same, but it is a better. So if you close the microphone to your
okay, let's try this. Okay, so as I was saying, so there are some assumptions. The second one is about the isothermal conditions. Then the material is behaving elastically, so the formation is fully recoverable, and we have a fully or nearly incompressible material. So meaning that during the formation, the volume remains constant. The hyperelastic models that we are going to see are usually not expressed directly via modulus and Poisson ratio, like what we are used to know and to see for metals, for example. But these constitutive hyperelastic models are usually expressed through the strain energy potential function. Before going into these models, let me just remind a few background that is useful for the rest of the presentation. There are two kinds of stress and strains, engineering and true. The difference is that engineering is actually assuming that dimensions of the specimen remain constant. So we are relying on cross-section area that is constant, that is the original one, and also for the strains. For the true stress and true strains.
Sorry, Matteo. So
yes.
So some students have the same situation. So could you change the microphone, or
sure.
Could you use the laptop directly?
Okay, I can try to use the laptop directly. Let me. Is it better now?
One more. So could you speak again?
Can you hear me?
Okay. This is very nice, I think.
Okay, so can we proceed this way?
Yes,
Okay.
it would be good.
Okay, let me see if I can still increase the volume, but is that better? Is that better now?
Yeah, it's okay. Thank you very much.
Okay, okay, great. So for the true stress and strains, the difference is actually we are considering the current dimensions of the specimen. So in this case, the area, for example, is updated time by time, and also the same for the length, that is in the end the result in this integral. If you also rely on the constancy of the volume, you can also have easy equivalence between the engineering and true stresses and engineering and true strains. Then for measuring, for referring to the deformations, we also have stretches. Stretch ratios, or simply stretch, are defined as the difference between, the current length of the material on the original length of the material. And there exist, of course, three kinds of principal stretch ratios that are related to the direction, the specific direction of your deformation. Finally, we have one third way to express the deformation, that is about and through the strain invariants. There are combinations actually of stretch ratios. You can see here the definition of those. They are scalars. Okay, so these parameters are able to measure the strain that is independent of the coordinate system used to measure the strains itself. So this is very much related also to the assumption of isotropic material behavior. And finally, we have the volume ratio. It is again something related to deformation, and it is defined as the ratio between the current volume and the initial one. So, and this is J is the way to refer to this. There are different forms of, for defining W, it is the strain energy potential function. And some of them rely on stretch ratios, and some of them rely on strain invariants. And then, of course, you can always derive stresses and strains are related to, with very simple mathematical calculations. The overall form of these hyperelastic models is the sum of two main contributions. One is the deviatory contribution, and the second one is the volumetric one. Because generally speaking, if you have a general stress state, what you can have is to separate the deviatoric stress that is causing angular distortion only, and hydrostatic stresses that are causing only volume changes. We are using the same assumption here so that we can have these forms that are a sum of deviatory and volumetric body terms. As I was saying before, there are several forms of this function, of this strain energy potential. They all require certain type of parameters as an input that are related to material constants, but the number and the kind of material constants are different. The choice of the most suitable function that is describing your specific material usually depends on the type of elastomer that is analyzed, the loading conditions, so the percentage of the strain, for example, as we said, mainly because of the Maulens effect, and the amount of available data, those are the kind of available data. In general, how to choose the best strain energy density function depends on the curve that is closest fit of stress strain data test. So the most suitable model is the one that is able to represent your experimental data, in other terms. In most challenging applications, then there may be only one model that works fine. In other cases, and most of the cases, you have different models that reach the same level of goodness. Now I'm going to show you the models and some also very general guidelines to use them. But of course, these are only guidelines. So these are not strict rules to be applied, and that can lead you directly to the best solution. These are actually part, not all the models that are available, hyperelastic models, but these are the phenomenological models. Then there are also others that are more based on statistics, but today we don't have enough time to see all of them in detail. They rely on the first, on invariance, on strain invariance, or on principal stretch ratios. They are suitable for nearly or fully incompressible hyperelastic models. These are in the green area. And these other two for more compressible hyperelastic models. They are also connected because, the polynomial one, for example, is the most general and also the most complex, but then by applying some assumptions, you can derive also other models. So we have here in the upper part, the most general and complex, and then some simplification, with some simplifications, you can derive all the others. Let's go a little bit more in detail on these models. This is the first one that we're going to see, the polynomial form. As I said, it is the most complete, actually, because you can really take into consideration everything in this model. It is based on the first and the second invariant, as you see here. And you may notice that there are some constants, C and D, that are actually the material parameters that need to be determined by curve fitting. We are going to see this in detail later on. There are some comments for, to add in, and also to as a guideline on the use of polynomial form. This is a very general form and can produce very good curve fits. And of course, the choice of n is going to determine the order for the polynomial form, right? So the higher is n, the higher is the order of the polynomial, but of course, also the higher will be the complexity of the model. With n equal to 1, actually, you're not able to represent all the inflections that we saw in a general stress-strain behavior of a material. So polynomial with n equal to 2 and 3 are usually used to see the deformations that reach 100, 300% of strains. Going beyond 3 is actually useless because, it is increasing complexity, but without really making a difference in the goodness of the fitness. This kind of form requires usually a good amount of data. So if you have limited data, so only maybe uniaxial test, you may consider other models. For example, the Monet-Riving model. It is actually is derived from the polynomial form with some simplifications, let's say. There are 4 kinds of models, Monet-Riving models, that are distinguished by the number of terms you are considering. So the 2-term Monet-Riving is only using the first and second invariant with order 1. And indeed, you can see that actually this model is equivalent to the polynomial form when n is equal to 1. The 3-term is adding the term that is coupling the effect of the first and the second invariant. The 5-term is adding the order, the second order. And in fact, it is equivalent to the polynomial when n is equal to 2. And finally, the 9-term Monet-Riving model is based on also the 3rd degree of interaction between the first and the second invariant. And it is equivalent to the polynomial when n is equal to 3. Some comments. Actually, they are the same that we saw for the polynomial form, since they are very much related to it. Some specific comments about the 2-term Monet-Riving model is that it is valid up to 90-100% of tensile strains, although it is not able to catch very accurately the stiffening effect. It is good to characterize the shear, but only up to 70–90%. And the compression behavior is not very accurate because it is only up to 30%. The Yeo model is also known as a reduced polynomial form because it is again derived from the more general description of polynomial form, but it is only using the first strain invariant. Okay, as you can see here, there is no I2, but only I1. And although you can use whatever degree, so n can be chosen, I mean, the number as you prefer the most, the cubic form, so n equal to 3, is the most used form. Some comments where actually this decision, where this assumption of the first invariant comes from. Well, you observed, the author of this model, observed that changes in the strain energy potential is less sensitive to changes in the second invariant than in the first. So he decided to propose a model that completely neglects this second invariant. And especially if there are very limited data available, so for example, it's only uniaxial test, it has been demonstrated that neglecting completely a second invariant leads to a better prediction. There are also, I mean, of course, the level 3, I mean, n equal to 3, the third order of the Yeo model is also implying the 3 constant, C10, 20, and 30. And they are, I mean, these 3 terms are there to consider, for example, the shear modulus, the second one for considering the softening that we have at small strains, and the third one to catch the behavior at higher strains where the stiffening is there again. The Neo-Hookean form is probably one of the simplest forms for describing the strain energy potential function, and it is also a good way to start with. So since the complexity is quite low, and if you don't want to start with something too complex, this is a good way to start with. It is not able, it's not capable to predict large strains, but it is good, for example, if your applications involve very small strains. And in this case, I mean, this Neo-Hookean form, the same consideration that we made for the 2-term only reading still apply here. So it is able to predict up to 30–40% of tensile strains. It's good to see also the shear behavior, but only up to 70–90 degrees, and the compression can be catched only up to 30%. The Ogden model is instead always a phenomenological model, but instead of being based on strain invariance, it is based on principal stretch ratios, as you can see here. And it is, again, equivalent to the Monnet-Ribin, so you can derive it through the Monnet-Ribin by applying some specific conditions. Some comments about the Ogden model. It is more accurate, maybe more accurate in describing the experimental data, since it is already based on stretch data, but it may be also more computationally expensive. And if there are limited data tests that are available, the curve fitting of this through this model may not lead to very realistic behavior. You can expect, if you are using at least 3 terms, again, a good representation of the model, because the experimental, I mean, the constants that are describing the model are able to represent, for example, small strains through the definition of alpha 1. The second term that is instead able to represent the stiffening at larger strains, and the third that is able to to help in representing the compression part. Finally, maybe, yeah, there are two missing. Other than models that are based on uncompressibility assumption, we have also a couple of models that are able to get also the variation of the volume. The Ogden compressible foam model is one of them, and you can see that it is very close to the Ogden model, but in this case we have this part, this parameter, that is coming actually from the volume ratio. So this is where you can see very clearly that there is a tight coupling between the stretching, I mean the ligatoric part and the volumetric part. And this is where we can see that the compression, the volume change is taken into account. The last model is LATSCO model, and it is again for compressible materials. It was specifically developed for polyurethane with very specific behavior. It is extremely simple, and that's why actually it is very much used, but it has many assumptions that should be checked, of course. For example, the most important assumption is that your material should have a Poisson ratio very close to 0.25. That is what is making this material very simple. But I mean, this is quite used, and specifically these two guys, Platz and Co, developed this model for 47% volume percent of polyurethane foam type rubber. So then what you still need, so after having, scrolling down all the models, of course, the mathematical derivation of those is not something of interest, at least today, but I included some references at the end of the presentation that you can use to go more in detail, or you may also contact me by email if you want to know more details on those. What you're still missing are the experimental data. We know that, and also some considerations that we made about the guidelines in using these models are related to how many data and what kind of data you have, right? So there are, generally speaking, 6 kinds of tests that you can perform to mechanically characterize the behavior of your material. The most used, and actually I would say the only one that is strictly required, is the uniaxial tension. That is also reported here in this picture. You need a universal testing machine where you can clamp your material, your sample, and then by applying a deformation, you can measure the resisting force that can be expressed as a stress, or resisting stress. This is the simplest loading condition, but then you also have this other 5, the equibiaxial tension, the planar tension, that is actually assuming that while stretching the width, I mean the side of the sample remains constant. Then you have uniaxial compression, so it is always in one single direction, but instead of being in tension, it is in compression. You have equibiaxial compression, and finally planar compression, that is the equivalent of the planar tension where you have this side that is considered constant. Note that for all the models that we saw in the presentation, the data should be collected and expressed as engineering stresses and strains. We saw the difference at the beginning of the presentation. There are also some good news. Actually, if we are assuming incompressibility, so we are considering the volume remains constant during the deformation, actually we also have this other simplification that can be applied. So if the Poisson ratio can be considered very close to 0.5, these modes of deformation are identical. If you see, for example, usually the equibiaxial compression is the sum of the uniaxial tension and the hydrostatic compression. But since this is something that we can neglect. These two modes are actually the same. The same applies for the uniaxial compression and the equibiaxial tension, and also between the planar tension and the planar compression. So as I was anticipating, these are some references and further readings that you may be interested into. You should have all received also these slides, this deck by email, so you can already, go through the slides and go into details. So, are there any questions so far? Because actually this concludes the theoretical part. Okay, so if you have any questions, that's a good moment. Then afterwards we will have I don't know, maybe 10 minutes break or something like this, and then we will use the remaining time for the more practical part. So let's say virtual hands-on part. Okay, so is there any question?
Okay. Are there any questions? Okay, Catherine, please.
Hi, can you hear me?
Yes, I can hear you.
Okay, good. I was just wondering, in my brief experience with hyperelastic modeling, I found that the data can be sensitive to the specific type of test used, particularly for biological materials. Do you find that it can make like large errors in the results of the modeling, or do you find that to not be an issue?
Sorry, can you repeat just the last part of the question?
Sure. Do you find the different data that is collected from the different types of tests used to have a large effect on the accuracy of the model?
So you mean about the testing conditions?
Yes. So for instance, if you tested with compression versus tension and you end up with different results.
Yeah, well, actually, yeah, this is a good question. This is something that I agree in principle. Usually the uniaxial testing is something that you should always rely on. This is maybe the most important because from one side, it is the easiest. And on the other side, it can be used to determine the most of the mechanical behavior of the material. For example, in my experience, also the compression tests that are in a way quite easy to obtain are also sensible to a lot of testing conditions, like, for example, what happens at the boundary condition. So, for example, when you apply a compression stress into a cylindrical sample, in principle, you should rely on the assumption that the sample remains a cylinder, but of course, it is not. You have a sort of barreling effect, and it induces, of course, some problems. My suggestion would be to rely at least, and in some cases also only, to uniaxial tests, but very carefully done. So, for example, instead of measuring the deformation or the current, the instantaneous length of the sample, instead of deriving data from the motion of the crosshead of your testing equipment, you should be able to add an extensometer or any other kind of equipment that is able to measure the deformation specifically of the thinnest part of your dog bone specimen. This is something that increases a lot the accuracy of your data. Then, of course, there are environmental conditions that are very much important. And also, as I was mentioning, carefully decide what is the protocol of your testing. For example, in the velocity on the application of the loading conditions, and also the amount of strain that you are going to apply. This is because of course, the Mullins effect, that is something that you will always have also when your material is going to be applied in your real robot. Does it answer your question?
Yes, that was very helpful. Thank you.
You're welcome.
Okay, thank you very much. Are there any questions? Okay. So, Matteo, would you have a small break?
Yeah, I suggest to have a very short break, maybe 10 minutes or so, and then we will come back and I will explain what the practical experience is about, and I will leave the rest of the slot to the students, to the attendees to perform the tutorial. And of course, I will remain here, for any other support or question, and we will go through them together if necessary, of course. Okay?
Okay, thank you very much. So, for you to restart?
Yes, I'm here. Can you hear me?
Yes. Okay.
Okay, good. So let's proceed. So as I was anticipating, now it's your turn. Just let me summarize the workflow that is using all the tools that I introduced and what you are expected to do in the next hour or so to perform this tutorial. So as you may understood so far, it is very important to start with some material experimental data. In this case, I'm providing you already some material, some data. And by the way, can you confirm that you received the file, the compressed folder with all the data? There are 4 Excel files and the PDF with the slides. Someone is answering, I think. Yeah, okay, so thank you very much for confirming. Okay, great. So yeah, so in general, you should start with some experimental data. We saw that actually the way you extract this data is a lot depending on the kind of deformation modes and magnitude you are expecting in your application, in your robot, in your system, okay? So these two, the way of designing the experimental tests is very much correlated to the data that you are going to extract. So these two phases are in parallel. For the tutorial itself, of course, I'm going to I already provided you the experimental data, and you don't need to make any choice on this, but just for you for completeness, I'm mentioning this. Then you need to choose your hyperelastic model. We saw 7 hyperelastic models. There are some pros and cons. I tried to summarize the most critical advantages and disadvantages. You need to use a curve fitting tool. In this case, we are going to use MATLAB curve fitting tool, but of course you can use whatever other tool that is able to accomplish the same kind of algorithms to evaluate and compare the hyperelastic model's capability of catching the real material behavior. This means that actually you have to go back and forth between these two blocks, several times, because you are searching for the best model that is fitting your experimental data. And finally, when you're happy with the hyperelastic model you choose, you have your virtual material. So you have a way to describe analytically the mechanical behavior of your material. And now you can use it wherever you like. So if you are having, for example, finite element models, You can use this representation as a library for your model. You can use, I don't know, some other codes, some other models that are describing the more complex behavior of a system, whatever you like. This is the basic knowledge you need to deal with material properties that are coming directly from your own material, so from experimental real data. Okay, so the tutorial is divided into a few phases. The first part is about the extraction and usage of material experimental data. You have this Excel file called tension uni Excel. This is where the experimental data that I'm providing you are provided, are stored. If you open MATLAB, you can use, you need to import this data as single vectors. You can use your own code if you like, or very simply, you can use these few lines to have, to create three vectors: the strain vector, the stress vector, and also the stretch vector. As you know, the most, actually, the strain energy functions are based on stretches or on invariance. But actually, in order to have, the fitting tool will work only on the stretching. So you have the description of these three vectors. Then you can open the curve fitting tool of MATLAB, and you will have this sort of new window with the tool. Then, this is the second phase, and it is about the hyperelastic model choice. We saw several models. Start with one, whatever you like, maybe also on the base of what we said about guidelines, but for the tutorial, I would like you to test all of them, so you can also go in order. First of all, you need to derive the stress-stretch relation from the strain energy potential, because the strain energy potential, of course, is a function that is related to some constants and to invariance, strain invariance. You need to derive the stress function related to the stretches, and if you like, also the strains. In order to do that, and since I only provided you uniaxial tests, you need to apply this equation if the model is based on strain invariance, or this equation if the model is based on principal stretch ratios. So you just need to perform a very simple derivatives, then substitute the definition of the invariance, and you will have a function of stresses that are depending only on stretches. It is exactly what you are expecting for the curve fitting tool. And in fact, once you have this equation, you need to go back to the fitting tool, the MATLAB fitting tool. You need to set the X data and the Y data as a stretch and stress respectively. Then you need to set in the custom, in the function description, custom equation, because you are going to type in directly the expression that you derived in the previous step. So here, instead of having this function, you need to type in the stress-stretch function that you just derived from your hyperelastic model. Then just be sure that in the fit options, robust is set to off and algorithm is set to trust region. That I tried several times, and it seems that this is the combinations that works better. Check that the autofit is on, and then let the tool calculate the fitness, the goodness of the fit. So you will see the fitting curve and some data that are describing how good the fitness is describing the experimental data. Then you can go to another model, and you can repeat all the steps that we saw so far in a new fit. So just clicking on the plus sign that you will see in the upper part of the tool, or you can also simply overwrite the current settings, the current equation that you set in the field, and evaluate a new model fitting. This is just to summarize the workflow that I showed you before, and this is the table that is expected to be filled in during this tutorial. I'm not sure you will have enough time to do them all, but one by one, this is mono-variably in two terms. This is the space to report to the function that you derived from the model. These are the output that you will receive from the curve fitting tool of MATLAB. And these are the constants, the parameters that are describing your model. Of course, not all the models need all the parameters. So some of these cells will be empty for sure. So for example, the two terms Moonley-Riebeing model only need C01 and C10. So this will be empty. But some others will use it. So for completeness in the table, I reported all of them. Okay, does it make sense? Is the assignment clear? If it is not, just tell me. Otherwise, I will be here for all the rest of the time. But you are free to use all the slides and the tool to go through this exercise. Also checking the question, the chat window. Thank you. Someone confirmed that the assignment is clear, but in case you have any other question, of course, I will be here. For Andrea Tigrini, we are sending you the email once more because probably there was a problem with the email.
Thanks, Prof.
No problem. Okay, so someone is asking if we are going to have a solution at the end of the time. Yes, if you like, I can provide you a solution, but not at the end of the tutorial, but at the end of the school, because actually in the overall assignment, in the working groups that you are going to have during the school, you are going to make use of these solutions, of this procedure. So I don't want to anticipate the solution. I would like you to at least to try your best to derive this information. After the school, if you are interested in the solution, just drop me a line. I will provide the solution. This table completely full. And yeah, I think this is the best way also to give you the solution. We stop sharing for the time being, just because I assume that you all have received the slides. But of course, I can I can resume it if necessary. When you are having the first results, just let me know so we can check if they are correct. So you can proceed to the next, knowing that the procedure is correct. Someone is asking for the units for the data. Well, actually, these are stress strains. So for the strain, of course, it is adimensional. So there is not a specific unit. For the stresses, they are taken in megapascal. But actually, in the curve fitting tool, you don't really need to indicate the unit of measurement. So it's just to let you know what are the realistic units, but maybe you shouldn't need this information anyway. Okay, let me manage some comments and private messages. So actually, Alberto made a question related to the fact that since we only have data related to the uniaxial conditions, is the first training invariant reduces only the term E1. Well, actually, the idea is that although you only have data related to one single direction, the fact that you can also rely on the incompressibility assumption, you also have some data related to the other directions. So both the invariance and the stretch ratios are affected by this. So you can use data coming from one single direction experiment for a more comprehensive evaluation of the overall behavior of the material. There's another question. Let me check. Okay, so another question is related to the difference between invariance and actually also stretch ratios with the bar on the top and without. Well, actually, the parameters that have the dash, the bar on the top, are the one that we are considering to be decoupled. So when we can decouple the deviatory information from the body information, so terms that have the deviatoric and the volumetric distinction are associated with the bar at the top. The other one are instead not including this assumption. It's another good question. Actually, of course, the models are expressed in their formal, complete. The way they are described is complete. So they are also considering the volumetric deformations. If we are assuming that J is equal to 1 due to the incompressibility of the material, the last term of all the models are assumed to be equal to 0, right? Because the volume ratio is 1, and whatever is the model, it is going to be nullified. Thanks to Lani for the question.
Hello, sir.
Yes?
Sir, is the principal stretch ratios the corresponding stretch from strains in the principal axis?
Again, sorry.
Are the principal stretch ratios lambda 1, lambda 2, and lambda 3 the stretch along the principal axis, that is XYZ?
Yeah. Okay, one single detail, because actually this may be misleading. Also, given some questions that I'm receiving. This is the, let me share the screen. I given that for granted, but maybe I shouldn't. Since we are assuming that the principal stretch ratio 1 is in the same direction of the testing condition, and by the volumetric constancy, we have the information about the principal stretch ratio 2 and 3 that are equal, and both equal to 1 on the root square of the principal stretch. Okay, is this what you are considering, right? Also for defining the, of course, the principal stretches themselves and also the invariants. I mean, I didn't say it especially in the slides, but this is the consequence of the constancy of the volume, the compressibility assumption. Okay, we have a winner. Actually, the first who solved the first model is Alberto Isaac Perez and Pablo. I can confirm that the material parameters that you derived are correct. So the procedure is quite the same for all the other models, maybe slightly different for the Ogden, which is based on principal stretch ratios, but the way the procedure is the same, and you can evaluate the goodness of the fits in all the cases. Okay, so in the last few minutes that we still have, I received a couple of requests to go through the process once more, just to, to clarify where some tricky parts would be. And let me share the screen once more. So you should have imported the material data quite successfully. At least it seems no one had problems on this. You also opened the curve fitting tool. Just let me go here. Probably here is the most tricky part so far. So I don't know if you started from my table from the first one, or if you went through them randomly. But the idea is that if you started with, for example, Mooney-Rivlin model, it is based on invariance, right? So you need to compute this equation, so the stress stretch equation, by substituting the model with n equal to 2, since it is the two-term Mooney-Rivlin model. You have the equation, you put it in here and here, make the first derivative of it with respect to the first invariant here and the second invariant here. Then you should have the entire equation that is still depending on the invariants. Then you need to substitute definition of the invariant with respect to the principal stretch ratios. And then you have to substitute the stretches, so the stretches that are in the input file with respect to the principal stretch ratio, the corresponding one. So it means that where you have principal stretch 1, you just need to use lambda, so your x in the curve fitting. Wherever you see lambda 2 and lambda 3, so the stretch ratios related to the second and the third direction, you need to substitute 1 on root square of lambda. And this is how you can derive the function in the case of train invariance. In the case of principal stretch ratios, it's simpler because you just need to make the derivative of the energy strain density function on the lambda, on the principal stretch ratio. And then you just need to put this equation that you found here in the custom equation field of the tool, make it fit, and see what are the degree of fitness, so that is related to this these 3 parameters. And in the specific case of the two terms Mooney-Rivlin model, what is the value for C01 and C10? That's it. Then you can proceed to the other models. I think this is what who of you was successful in finding the right constants is what they did, and what you did to find the right way. Check if there are other questions in the chat room. Let me stop sharing, otherwise I cannot see that. So there are questions.
Sir, I have a trivial doubt. So
Yeah.
what is the meaning of this I1 bar in the two-term Mooney-Rivlin model?
What is the meaning of?
I1 bar.
You mean the sign that is at the top?
Yes, yes.
So it is related to the deviatoric or the volumetric distinction that we made during the general part, the theoretical part. The only model that is not relying, there is only one model that is not relying on that, where the assumption of the division between the two kind of terms is not used. For all the rest is just to identify that that is related to a principal stretch ratio that is coming from the assumption of a division between deviatoric and volumetric terms. Okay, so I think the time is over, but I see that there are still questions. Unfortunately, I'm not sure that the chat will be maintained, and I'm really not able to answer all your questions now. If you like, I can answer your questions offline. I mean, maybe by email. If you can just send me an email here, I'm typing in the chat my email once more. So maybe after lunch, because I think we are going to have a lunch break now or something like that, I will manage all your requests, not by email, because actually I cannot manage all the questions in the chat before it is going to be closed, and for sure it will be erased. So please send me an email and I will reply you as soon as possible, and I will be happy to answer you as soon as possible. Okay, thank you very much, and I think we can close here this tutorial. So, Professor Hirata.
Okay, thank you very much, Matteo. So this is a very, very informative talk and a workshop. So thank you very much again. So, okay, so